Hello again, folks. It's Mr. LaRusso once again. Today we're looking at Newton's universal gravity law. Okay, so let's talk about what Newton's universal gravity law is. First of all, we're familiar with one form of gravity, and that is the term that we use called weight. Now, before this, we defined weight as the force of gravity is equal to the mass of an object times little g. Now, on Earth, little g represents the acceleration due to gravity, which is 9.8 meters per second squared. The force of gravity is measured in newtons and our mass in kilograms. And this is what we have been working with in terms of the force of gravity up until this point. Sir Isaac Newton, however, speculated, and well, in fact, did better than speculate. He was able to show with significant mathematical accuracy that gravity was not just the dominion of large objects such as planets, moons, asteroids, etc. He discovered that gravity was generated by any object that had mass, which is a pretty incredible revelation. So many of you heard the sort of the story that he was sitting under an apple tree and an apple fell on his head and he's like, aha, eureka, I discovered gravity. Well, it didn't obviously quite go down that way. That's the legend. It is said that when he was observing the moon in the daytime sky, an apple had fallen from a tree, but it landed on his stomach. And then it led him to understand or question, what was it that the moon and this apple have in common? When you really think about it, that's a pretty intense question. Like, what does a moon and an apple have in common? And what he realized is that the only thing they had in common was the fact that they possessed mass, which is a pretty, esoteric thing to come to the conclusion with. But that's where he went from this. After an irresponsible amount of mathematical manipulation and astronomical evidence, he was able to formulate the following formula. And that is the force of gravity, which is the same as the force of gravity we've been working with before, is equal to this symbol big G, which stands for the universal gravitational constant, the mass of our first object, the mass of our second object, divided by the separation distance of the two objects squared. And this applies for any object, whether it is planet-sized or if it's the size of a dust particle. All of these behave in the same way. So what are the big ideas with this? Well, the big ideas, and these are the real key ones, is that the strength of gravity is directly proportional to the mass of each object, which means if one of the objects, if their mass doubles, that force of gravitational attraction doubles. And it doesn't matter which one doubles, as long as one of them doubles. If one of the masses is cut in half, then the gravity is cut in half. If both are doubled, then that effect is times 4, because 2 times 2 is 4. So the intensity of gravity would increase by a factor of 4. If both masses were cut in half, the intensity of gravity would be cut down to a quarter. But what's very interesting is the behavior of what the distance does. Now, notice, instead of using the letter D, I'm using the letter R. There's actually a good reason for that. So R represents the distance between the centers of masses of each of the objects. And you see that it is squared. That is very important because what that means is if we double this distance separating the two objects and you square that amount, that decreases the strength of gravity by a factor of 4. So if you double the distance, gravity is cut by 4. If you triple that distance, gravity is cut by a factor of 3 squared or 9. So let's do a fairly simple example. Let's go off to the side here. So let's say we have two objects, all right, one larger than the other. And let's say that they are separated from center to center. Let's get some statistics here. So let's say this is our mass 1, and it's equal to 10 kilograms. Let's say our mass 2 is equal to 20 kilograms. And let's say this distance separating them is 5 meters. All right, to figure out the force of gravity, the force of gravity is equal to G, M1, M2 over R squared. All right, well, first of all, this value G is called the universal gravitational constant. And this constant is actually one of the more complex numbers to calculate. And every year it actually gets further refined. And it's based on astronomical calculations. And Sir Isaac Newton in his day actually didn't know what this value was. There was no equipment sensitive enough or experiment or technology available at the time to calculate it. So even though he came up with this formula, he was never able to actually calculate any forces of gravity, but he could use proportioning to get relative strengths of forces. So big G, the value is 6.67 times 10 to the negative 11. And I have an absolutely ridiculous way to remember that. In London, Ontario, the phone number for Pizza is 667 1111. So I call this the Pizza constant because it's 6.67 times 10 to the negative 11. So that's an easy or easier way to remember that number as the Pizza constant, which makes sense because eating enough of that pizza will increase your gravity significantly. Any case, I digress, and terrible jokes notwithstanding. All right, so now the mass of our first object is 10 kilograms. The mass of our second object is 20 kilograms. And the distance separating them is 5 meters, but it's 5 squared. It's very important. So the value of this works out to 5.336 times 10 to the negative 10 newtons. This is a very small amount. And that's the thing. Small objects produce such small gravity that we don't really notice it on our everyday lives. How much would something like this on Earth, how big of an object on Earth would be required to generate something that small? And you'd need an object that is 5.4 times 10 to the negative 11 grams. Well, a microgram is times 10 to the negative 6. A nanogram is times 10 to the negative 9. So times 10 to the negative 9, that would be in the billionths of a gram. We're talking just a tiny amount. This is times 10 to the negative 11 we're talking about here. So we're really talking about 0.05 nanograms, and absolutely indetectable. So the amount of gravity between small objects is really quite negligible. It's not until the objects get very, very large. For example, when one of the objects becomes the size of, say, a planet, like the planet Earth. Now, Earth produces an absurd amount of gravity because the mass of the Earth is approximately 9.971986 times 10 to the 24 kilograms, which is pretty enormous compared to the mass of everyday objects. Well, and again, what if we double that distance to 10 meters? Gravity then becomes 1.334 times 10 to the negative 10. And that, if you were to compare those two numbers and take the ratio, we double that distance. This is actually a quarter of the size of that original force. So the moral of the story is that the distance is more of an important factor than the actual masses themselves. Changing the separation distance between the objects drastically changes the strength of gravity. As you move further away, gravity decreases in strength as the square. Hence, this is called the inverse square law. All right, so here are the big ideas. First of all objects that have mass produce their own gravity. As mass increases, the strength of gravity increases. As the distance to the object increases, the strength of gravity decreases by the square of that distance. Now, this notation up here, this is the standard notation, which you will see in most books. Sometimes you'll see the R represented as a letter D. And I still haven't explained why I'm using the letter R. I will do that shortly. I, however, have a slightly alternative notation to this. Instead of using M1, M2, I sometimes will use big M and little m, especially if the objects are greatly varied in the size. Big M would be, for example, your planet. Little m would be something like a satellite or a meteor or something smaller, even you as an individual. There's a reason why I use this particular notation, and that has to do with our original formula for the force of gravity. Now, the force of gravity, the original formula was little m times little g. Well, on Earth, that little g is 9.8 meters per second squared, but that's only on Earth. Not every planet has gravity of that strength, and even that varies depending on where you are on Earth. Now, on the surface of the Earth, it varies very little, but as you get higher and higher, say, for example, up by the International Space Station, the acceleration due to gravity is significantly lower. Fg stands for the force of gravity, and that is in newtons. And m, this represents the mass of the object. We're looking for the weight of an object. That's what little m stands for. Well, using my version of the notation and this one, what you're going to notice is this. Both of them have a little m in common. Because in the universal gravity equation, one of these m's is u, or some other object that is on the surface. By using this notation here, it makes it clear which m is which. And there's an advantage to doing this. because then we can set these two equations equal to each other. So let's say our original equation is number one, Fg is equal to little m, little g. And our second equation is our new one, Newton's universal gravitational law, which is equal to g big M little m over r squared. When we set them equal to each other, we get mg is equal to g big M little m over r squared. But what you notice is that, and of course I accidentally had my line in the wrong spot, is the m's, I should say, cancel out. And what we're left with is g is equal to big G big M over r squared. And this formula here helps us actually determine what the acceleration due to gravity is on any given planet. So for example, the mass of the Earth is 5.971986 times 10 to the 24 kilograms. Now, the r in this case stands for the radius of the planet. Now you'll see why we refer to as r. Because remember, this is measured from point to point, from the center of mass of one object to the center of mass of another object. While on Earth, we sit on the surface. And the distance to the center of the Earth is 6.371008 times 10 to the 6 meters. To further illustrate this idea, if this is planet Earth, the center of mass of the Earth is there. If the object, say you, are on the surface, the distance from center to center, well, that represents the radius of the planet. Hence why I choose the letter R. Well, using this information here, we can calculate what little g is. G is big G, big M over r squared, which is equal to 6.67 times 10 to the negative 11 times the mass of the Earth, which is 5.971986 times 10 to the 24, divided by 6371008 times 10 to the 6, all squared. And that works out to 9.81 meters per second squared. And there you have it, Newton's universal gravity law.